started. Last class, I introduced the problem of congestion control, TCP congestion control. This is like a top 10 problem in computer networking, one of the very important problems in reliable transport, right? We're going to spend all of today's lecture, possibly a little bit more, before we move on to the network layer. That's the next chapter. Programming assignment 1, project 1, thankfully over. I hope you guys had a good experience overall on average working on it. I know some of you had a frustrating time, but looking at the numbers on Gradescope, it looks like most of you did pretty well, right? A team named after a car, an 83 Corolla seems to be the topper, so congratulations. We haven't yet redone everything, but looks like it's pretty consistent. And then another team, for lack of memory, I'm going to call them blipping sockets. That was like number 2. And then a whole range of whole bunch of other teams. So I hope you enjoyed the gamification aspect of it. It was it added to your wanting to do well. One thing I'd like to add is there is a small, we actually got about as many submissions as just a homework or lab, which is great. Project 1, basically, or 1A, basically anyone who submitted, or not anyone, but like 90% of people who basically submitted got 100. 1B won't be quite like that, but at least half the class or more will get 100 of 1B as well. We're still finalizing what to adopt, getting full, but if you don't get full, it doesn't mean that you'll lose a lot of points. It'll be a very gradual degradation from there on. So basically, the class did great on project 1 from my perspective, on average, of course. There's however, indeed a small number of you who either didn't submit or just haven't been able to do justice to their project 1. And if you feel, so the deadline's over, the course is paid such that we will keep moving. However, if you feel an impulse to win the fight, to get it actually to work, by all means, I encourage strongly that impulse. We'll be happy to help you with your code. I'm not going to be forcing, I don't actually have like a recommended sample solution for one anyway. There's a whole bunch of strategies you could do, and different people do different creative things. So if you still want to give it a fight, just to get it working, to improve your learning, your knowledge of software programming, I strongly encourage that. We'll be happy to help you get there, right? Irrespective of whether that has an influence, a positive influence on your grade or not. Okay, reverting back to the last topic of the day, TCP congestion control. I introduced this problem at the end of last class with this plot, this really scary looking plot, right? So in the Bay Area, they have this network with 400K kilobits per second or so of expected capacity. So this is the output or what's coming out of the network. We'll look at a few graphs later, input versus output. This is what is going into the network, right? Normally, the faster you send, the faster things will come out of the network on the other side. What you expect. However, if you send too fast, you can break the network. That's our congestion control problem, right? It's different from flow control. It's much more complex problem in flow control. In flow control, we're trying to not overwhelm the receive. That's just one entity. It tells us through its receive window how much it can go, right? But the network is a much more complex object than one receiver. And so what they observed, so they didn't really think of congestion control. They just basically had reliability mechanisms in TCP, which is about correctness, and they got all that pretty right? They got all that right from the start, and it was working all pretty well until like the mid-80s, because there wasn't that much demand, that much traffic. People weren't experimenting with different applications as much. But it got to a point where they learned the hard way that this is the behavior, that they were getting less than 20% of the capacity of the network. They were getting less than 1% of useful work out of a network. This is really bad if your cable modem service provider tells you, hey, you have a 20 Mbps connection, and most of the time you get less than 1% of it, which is like barely 200 kilobits per second, you'll be mad, right? You want something better out of your network. That's the congestion problem. That's what can happen if you don't slow down. So in order to operate at a good point, you need to, which is a fast point from the network, the overall network's perspective, each individual TCP sender needs to slow down. And that's what we're trying to understand. Why do we need to slow down to be faster? How much do we need to slow down? And if you slow down too much, you just slow the output out of the network. So what is this optimization problem, right? What are the trade-offs here? That's the question of the day. Okay, so there are a few causes of congestion. We're going to look at them carefully. We've seen some of these while studying the principles of reliable transport, timeouts, false timeouts, and so on. But let's look at these step by step in a little more detail. Here's a very simple scenario of a network. Okay, there's a router. I think I'm going to come that side. Here's a network, a very simple network with just a single router that has 4 hosts attached to it. And we're going to assume here that the buffer, in the starting example, in the first example, the buffer here has infinite capacity, okay? And the input and output links of both are. So there isn't anything complicated going on here. There's not a bottleneck, queuing what high capacity link followed by low capacity. Nothing complicated going on. There's just one router, links are uniform on both sides. We'll just assume that there are 2 flows, okay, to keep things simple. And we'll assume infinite buffers, of course. Okay, that's already stated. Okay. We'll denote what goes into the network, so like the input here, we'll denote that by lambda n. What is lambda n? That's what your application is pumping into the network. So in project 1, the server is writing back into the network. Your client is also writing some requests into the network, but that's very small. The server is doing most of the heavy lifting of data sending. So that's what's being pumped into the network. And lambda out denotes what's coming out of the network, right? Ideally, you want lambda in to be equal to lambda out in reliable transport. Whatever you pump in has to come out. Which, if you have a correct reliable transport protocol, whatever you pump in from the side will eventually come out. It's staggered over time, or it may take some time, but eventually it will come out. Okay, so that's just reliable transport. But getting this right involves a little more when multiple flows are competing for the same resources. So in this example, we have 2 flows A and B, right? Okay, so this is the original data, this is what's coming out. We refer to lambda out as throughput. We also use the word throughput as a very generic term. That's just a bits per second bandwidth-like term. If you want to explicitly distinguish between sending rate versus what's coming out, we often also use the term goodput. Goodput is what's actually usefully coming out of the network. Throughput could mean that, or throughput could also mean just whatever is flowing through the network, like whatever, or including whatever rate is sent. These terms are used a little bit ambiguously. Okay. Okay, so we'll assume in this starting example, no retransmissions are needed. Okay. Then the question is, what happens as lambda n, the sending rate of each of the 2 flows, A and B, or by hosts A and B in this example, approaches R over 2, which is the capacity of the link. As each of the 2 flows approach R over 2, the total sending rate is R, right? That is the capacity of the network. We have seen before that as we go close to capacity, problems start to occur. We've seen queuing delays sort of go like that, right? For example. So that's what's going to happen. This first plot shows the queuing delay. It shows you the throughput, how the throughput behaves. As you pump in more into the network, you get more out of the network. That's the good part, right? What you expect in an ideal system is once you reach the capacity point, if you try pumping in any faster, you won't get anything more faster. You can't pump in more fluid into a pipe than it's carrying capacity, right? But what you do expect is it will go up and then saturate like shown in this picture. So as you increase lambda in, lambda out keeps on growing until lambda in, as once it approaches R over 2, what comes out of the network is a total of R, right? There's two senders, that's why R over 2 input from each gets an output of R total out of the network, or R over 2 each, right? Okay, that's the throughput behavior. What does the delay behavior look like? We've seen this delay curve before. As you approach capacity, delays approach infinity. Why do delays approach infinity? As you approach capacity, the queuing delay is going to grow in expectation to infinity. Okay? This router has infinite buffers, so there will never be a loss in this example. That's why no retransmission is needed, like it says here. As more and more data keeps coming in, if it can't push it, if the router can't push the data out fast enough at the rate it's coming in, it'll just keep on buffering it. It has an infinite buffer, so queuing delays will keep on increasing. Okay, so that's what's happening here. So that's the first cause of congestion, where delays simply increase. Now throughput, of course, by the definition of capacity, will get saturated at some point. If life actually behaved like this, throughput saturated, as you approach capacity, delays became really big, it would be a pretty good world. We wouldn't have a complicated congestion problem to solve. Unfortunately, this is not all that's happening. There's a few other things that's happening in this network that makes this problem much more puzzling. And that's why a lot of research has gone into this problem over decades, and it still continues to see active research. Okay? That's the second cause of congestion. Here, we will become a little more realistic. In practice, of course, you don't have infinite buffers. When you have finite buffers, routers have a finite amount of memory. Okay? So memory routers are much more expensive than some machines because it has to operate. It has nanoseconds to work on a packet, right? On the GBPS network, gigabits per second, you have nanoseconds to work on each packet. So if you have finite buffers at the router, the sender, occasionally there will be a loss because when the buffer is full, what can the router do if a new packet arrives? There's not any room, it's going to drop. This will trigger a timeout of the sender at some point. The sender is going to retransmit. And at this point, you have one more parameter than lambda in and lambda out. We will call this lambda in prime. Lambda in is what the application is trying to write into the network. Lambda in bits per second, that's the rate at which the application is writing. Lambda in prime is the effective rate that the network is experiencing. This effective rate lambda in prime in general will be greater than or equal to lambda in. In general, there can be loss. If there is loss, it will be greater because loss induces retransmission from the sender. So the application is trying to write, let's say, 10 megabits per second, but 1% of those packets need to be, let's say, retransmitted. Then essentially in the network, you're writing 10 megabits plus 1% of 10 megabits. Okay, so whatever that is, I guess 10 megabits plus 100 kilobits. Oh, 10 megabits per second plus 100 kilobits per second. 10.01 megabits per second. That's what's effectively being written in the network. And the graph for that, if you have perfect knowledge, when the sender only retransmits, or the sender only needs to send when there's enough buffer space, it's going to look like this. This is an example where the packet successfully got through. Sorry, did I screw up the animation? Okay. So that's, oops. If the sender had perfect knowledge where it would only send a packet if there was enough buffer room, the graph would look exactly like before. Lambda in is equal to lambda out until lambda in approaches R over 2. Okay. However, if it didn't have perfect knowledge, that is, sometimes it will send a packet and the packet ends up getting dropped because the buffer is full. Then here's what you're looking at. Packet goes out. At this point there's no buffer space. These are beautiful animations in the textbook. They take a while though. I didn't have time to make them fast. I did. So this packet got dropped. At this point the sender is going to retransmit. The At this point, let's say there's free buffer space. So this packet is going to successfully reach the destination. So the initial transmission failed or got dropped because of lack of buffer space. The retransmission succeeded. Okay. Now you see there's a difference between lambda in prime, the effective rate that the network is experiencing, and lambda in, the original rate at which the application is sending. So our graph now, the plot, the lambda in versus lambda out plot, looks a bit different now. It looks like it's shown in this picture, where as you increase lambda in, lambda in prime, lambda in versus lambda out remains the same as before. Okay, that's just reliable transfer. They'll be equal. Lambda in prime, the greater amount of effective traffic the network is experiencing. Under light load, it looks no different from lambda in, the original data. There's no retransmissions are needed under light load. Okay, but if you keep on increasing this load, at some point packets start getting dropped. Probability of a packet encountering a maximally full buffer increases, and so loss probability increases. And so those lost packets need to be retransmitted. And therefore, you no longer have the nice 45-degree linear relationship between lambda in prime and lambda out. What they're saying is what comes out of the network is less than what is being pumped into the network. Because some of what's being pumped into the network is duplicate data. So the more the curve bends down, the lambda in prime, the effective rate versus lambda out, the more it bends down, the worse your protocol is. Because you're doing more work to get the same amount of output, the goodput out of the network. Okay, so this is one cost of congestion. This is the realistic cost. This is finite buffers, not like the infinite buffer abstract example before. So this is one cost. This is not the only cost of congestion. We have elastic weighted capacity, as I said. We now have another problem, which is the previous problem we just saw was a problem where packet got lost, timeout happened, it was correctly detected as lost, and then retransmitted. With timeouts, we've seen one more problem, which is false timeouts. Sometimes a sender may time out just because it's too impatient. You sent a packet, you didn't get an ad, you couldn't wait long enough. There was actually no problem, but you decided you can't stand it and you retransmitted. So in this case also, there's retransmission induced additional work, but in this case, the retransmission was useless. In the first case, loss required retransmission to be patched. In this case, there wasn't even a loss, but a false timeout caused retransmission. And so, that's a pictorial view. This is the first copy of the packet. This actually had free buffer space. It went through just fine to the other side. False timeout happened. Same copy of the packet got sent, and both copies got to the other side. Correctness will be maintained. We've seen that the value of the timeout, there's trade-offs. Too high has a problem, too low also has a problem. So we choose, in TCP, we choose it to be the smooth transfer time, the exponentially weighted moving average smooth transfer time plus 4 times deviation. But sometimes that can trigger false timeouts like here. Now to include false timeouts, that lambda in prime, the effective rate being pumped into the network versus lambda out, what's the useful work coming out of the network? What work is the network doing? What work is the receiver seeing coming out of it? It dips, it bends further down, even more further down. One part of that reason is unnecessary duplicates. That's one part of the reason it's bringing down by some. And the second part of the reason is just like before, necessary duplicates. If there's loss, you have to retransmit. Sometimes even if there isn't loss, you have to retransmit. And they both bring down the efficiency of the network. Okay, so the network has to do more work to get the same amount of output, goodput out of the network. So these are two fundamental costs induced by retransmission, congestion costs and retransmission. This still doesn't quite explain why this can happen. you look at this figure, this seems like, okay, it comes down a bit, comes down a bit more for another reason. So let's say the loss probability is 1%. I don't know, how much do you expect loss, right? Most of the packets, most of the time, should be getting there fine. So how much can loss probability be? And how come, at the end of the day, what comes out of the network, how can it be 1% of the capacity? Like, it's coming down because of retransmissions, but how does it get here? If it gets like this bad, what it means is 99% of the capacity is just going somewhere, we don't know. We need a good reason for why this can happen. So think of an analogy in a real world queue, right? In the real world, let's imagine a cinema, a theater. People are going for a movie. When close to movie time, there's generally a queue build-up because a lot of people show up just before, they're buying tickets at the counter, and they line up. And let's say the person at the counter takes 30 seconds to process one customer. So their customer processing rate, the hour bits per second, I'm running an example here, is 30 seconds per customer, right? Hour bits per second or 30 seconds per customer, they're interchangeable, right? Or they're comparable metrics of how much work can be done by a router versus this ticket counter person. Queues build up. Queues are also in practice not infinite. Let's say there's a bounded queue, and the theater says, okay, if you can't keep customers keep standing beyond this point because the municipal code says we can only extend up to that or something like that. So if people, if anyone arrives after that, they'll just go back and maybe reattempt to join the queue later, right? You can make up your example, a cinema, or it could be like a bar or whatever. The question is, no matter what kind of queuing and going back, retransmissions happen, how is it possible for customers to not be driven into the theater, that's useful work, at the rate of 30 seconds per customer? In 5 minutes, how can this guy not push in 10 more customers? Whereas it's like saying something so bad happens that instead of 30 seconds per customer, pushing them at that rate, this usher is taking 3,000 seconds per customer. They're pushing one customer per hour or something like that. What is happening? How can this happen? Why is this usher's work going waste? Why is there this much waste? How could it possibly happen? Any guesses? Any reasons? Any ideas? Yeah.
Maybe there are so many unneeded duplicates that like the majority of the packets going through are unneeded duplicates, so the like effective rate would be a lot lower.
Yeah, what's your name?
Maxwell.
Maxwell. Yeah. So Maxwell's answer is, okay, so we're just building on the reason we just saw, which is there's so much duplicates. Well, in the theater example, it's a little hard to extend that analogy to duplicates. What exactly duplicates mean? People will go back, go home, come back after some time. The answer is there's so many duplicates that the effective rate is reduced. But this says that the effective rate actually comes down below the router processing capacity. This person is still doing work full time at the ticket counter. So no matter like if customers repeat, well, I guess the analogy breaks a little bit in the cinema theater analogy. But it's very difficult to answer this question of why or how it can happen if there's only one router. If there's one router, it will always be pushing out packets at its capacity rate R. Some of it will go down because of duplicates. It's hard to imagine a 99% or nearly 100x decrease in throughput unless people are transmitting 100 times, retransmitting 100 times more packets than they intended to. So they have to retransmit each packet instead of sending it once, they have to send it 100 times. That's a really, really bad point to operate at. Okay. That actually doesn't happen in practice. It's not like senders are trying to send that aggressive. They'll get the idea that things are not getting through at the same time. They will slow down in practice. That is what congestion control is trying to get them to do. But even if they send indiscriminately, it's hard to imagine how that much work can be wasted. To understand why that can happen, we need to make our network example a little more complicated. So we need more than one router. So the single usher example in our pager-like scenario doesn't explain why you're not pushing in customers at once every 30 seconds. Once every 30 seconds, a unique customer should be pushed in. Once they're pushed in, they're not going to come back in, they're not going to be transmitted. So it doesn't answer the question of why is this usher's work getting wasted. In a multi-router network, you can explain why this can happen. So in this example, you have 4 senders, you have multi-hop pods. It's not just a one-hop pod, or technically a 2-hop pod, because this one hop is a router from the host, right? But a single router pod. Here it is multi-router. We have timeouts and retransmissions. You have finite shared buffers by multiple flows. Again, you have your lambda ins and lambda in primes. Lambda in is the original, lambda in prime is the effective. And you have multiple flows like before. 4 senders, they're sharing these bottleneck links. In this example, this is 4 senders total. In this example, what can happen that can affect the relationship between lambda in prime and lambda out significantly, where lambda in prime can come down to like 1% of the expected lambda out of the original lambda in. The reason that can happen is because of the multi-hop nature of this network. So in this example, that second router you see there, that's like a second usher. There's 2 theaters. They have to cross like 2 steps before they actually get usefully into the theater to watch the movie. In this example, what can happen is this router may be doing a lot of productive work. So it is indeed sending, let's say this router's capacity is 10 megabits per second. It is indeed pushing packets out at 10 megabits per second. But if this router is so congested, because this sender is sending this red traffic is just incredibly high, it is possible at this router for 99% of whatever packets arrive at this router to be dropped, just because the load on this router is 100 times more than its capacity. So what that means is almost all of the work done by this router is going to go here and get dropped. This is something that doesn't really happen in a single router example. Whatever gets out has gotten out. There's good work coming up. But if almost all of the work being done by this router is going to reach here along the blue flow, and it's only going to get dropped here, this means most of this router's work is wasted, because the sender has to retransmit all over again in this blue flow. That's how you can have this in a multi-hop network scenario. You can throw away almost all of your capacity. Okay? This cannot be explained in a single hop scenario. This level of degradation will not happen in a single hop scenario. Useful work will still be coming out of a single router. So this router is always pushing packets at 100% of its capacity, but 99% of what it's pushing is getting dropped here. And essentially, this congestion affects this router's congestion ends up affecting this router and ends up wasting its capacity. So if you could make this more complicated, there could be more flows coming like this and maybe going like this somewhere else, and this router's work would be getting dropped at the further router. It's going to have this ripple effect where most of the routers could be doing useless work because these packets go a little ways only to get dropped later, right? So this wastage of work because of this ripple effect in multi-hop networks, can really exacerbate or exponentiate this problem. Okay, that's what leads to disasters like this. And this wasn't obvious to people in the beginning that networks could behave in these weird counterintuitive ways, that you could have this much of a reduction in good work or wastage of resources. So these are the costs of congestion. And you could extend that using congestion driver and so on, right? So as lambda n increases, all arriving loop packets in the upward queue are dropped, loop throughput goes to 0, and the ripple effect of that is what's causing this problem. Okay? So when packets are dropped, any upstream transmission capacity and buffering for that packet was wasted, would have been wasted. So how do we deal with this problem? Well, intuitively, what do you want to do? If you have some signal that you're sending too fast, then you slow down. Because if you don't slow down, this can happen. So what is that signal of sending too fast? That is what determines different flavors of TCP congestion control. You're going to see how standard university use TCP uses what ideas it uses, and then we'll see some modern variants of it, right? This is a summary of congestion insights. Throughput of a network, or what useful work. Here throughput means good put, and that can never exceed the capacity of the network. Delay increases as that capacity is approached. Loss of retransmission, loss-induced retransmission, as well as corruption-induced retransmission. That's implicit, doesn't say that here, right? Any loss-induced retransmission is going to bring the effective throughput down. False timeouts or unneeded duplicates are going to bring effective throughput down one more step further. And then in multi-hop networks, upstream capacity can be wasted because of downstream congestion. These are all the different causes of congestions that we need to keep in mind. So how do we do that? Well, we need some signal. We need a signal of I'm sending too fast and therefore I must slow down. And at a high level, that signal is what distinguishes various families of congestion control. We know a lot about congestion control over the past few decades, right? There's different families. The most important one, the way TCP does it, is called end-to-end congestion control. End-to-end just means end hosts, one end host to another end host. The end host is where the code, the logic, the design of the reliable transport is implemented. The sender FSM, receiver FSM, and RDP protocols, that's the reliable transport logic. Where is that running? Not in routers, it's running on my machine, on your machine, the end hosts. Routers and the internet are dumb devices. They just forward packets. Very simple entities. Our machines are very sophisticated entities in comparison. Okay, so all this TCP logic of slowing down, speeding up is implemented in our end hosts. End-to-end congestion control involves inferring that a problem situation is happening in the network. What are problem situations? Loss and delay. Packet can be lost. It can also be lost by corruption, but congestion is the more severe beast, because corruption is low probability. It won't have this kind of an effect. So there's a congestion-induced loss, or if the packets are not getting lost, but queuing delays are building up, and so delays are increasing, that can act also as a signal that you are slowly overloading the network. This is like traffic at peak times, especially like at exits or entries, or before a bridge or something, queues build up. That's a sign of increasing congestion, right? There's no analogy to loss in road networks. It's not like you queue up before a bridge, at some point your car just gets thrown into the Connecticut River, right? That doesn't happen in the road network. That can happen in the packet network. Okay? We infer these signals of congestion at the end host simply by the act of sending packets, watching out for their acknowledgements, and then looking for whether acknowledgements are coming as expected for the packets you're sending. And of course also coming in a timely manner for the packets you're sending. The round trip time is estimated by sending a packet and looking at, since I sent this packet, how long did it take? If this inferred round trip time is increasing, then you know that delays are increasing in the network. That's a problem scenario. A loss is basically an infinite activity, right? It's just, if you never get back an act, then that means at some point you say, you don't wait till infinite time, at some finite timeout, you say, okay, it's lost. In TCP, you have another signal of loss in addition to a timeout. You sometimes don't wait for a timeout to decide the packet is being lost. What's that additional signal in TCP? Timeout can be a long time for TCP to wait to ensure that a loss has happened. Yep. Triple duplicate act. That's a fast, also called a fast rate transmit mechanism. Fast rate transmit in TCP is a mechanism to detect loss earlier, potentially much earlier than a timeout, by using triple duplicate acts as an inferred signal of loss. It doesn't mean that the packet is actually lost if you get 3 duplicates, necessarily. But TCP decides 3 duplicate acts means this much reordering is unlikely, so I'm going to just call it a loss at this point. Okay? Now, end-to-end congestion control is not the only way to do things. There have been other congestion control approaches that have been both researched and deployed in practice. The internet's TCP uses end-to-end congestion control, but telephone networks have been operating for a long time from before the internet, right? They're over a century old, and they use circuit switch mechanisms, not packet switch mechanisms. And there, in that context, congestion can happen there too. It's much less of a problem than packet switch networks. But in those types of networks, like ATM networks, for example, that are circuit switched, people have studied network-assisted congestion control approaches. Even in the context of internet, people have studied network-assisted congestion control approaches, where network-assisted means routers are actively telling you stuff. It's not that the end host, routers just passively forwarding packets or dropping packets and end hosts are inferring like in TCP. Routers are actually collaborating with end hosts, with the end host TCPs, saying, hey, I'm congested, don't send packets too fast. That's called network-assisted congestion control. That's been explored in the context of the internet stack, network protocol stack as well, but the way we do things, the approach that's won the day is end-to-end congestion control. Okay? So this is network-assisted congestion control. Routers providing direct feedback to sending or receiving hosts with flows passing through when the flows pass through congested routers. Right? Here there's a data in ACK, and instead of just looking at the time since the packet was sent to the time the ACK arrived, or after a timeout saying the ACK never arrived, so it's lost, the router may explicitly convey this information to end hosts saying, don't send too fast because I'm dying out here. Slow down. So this can result in a more accurate inference at the end host for congestion. It can allow congestion to be proactively detected. You can respond more accurately. You can respond exactly. If the router says, this is where I am, this is where I am, this is where I need to be, the end host gets a very concrete signal. The end host can collectively get a concrete signal of how much to back off, as opposed to the network not giving them any information and the end host having to infer it all on its own, just by packets and packets. So network-assisted approaches have the promise of being more accurate and more responsive in congestion control, and these examples have been studied in the context of circuit switch networks, the telephone network, as well as the internet. But in practice, in terms of deployment, in the internet, end-to-end congestion control is what has been actually deployed, right? In TCP, that is TCP's congestion control. Now we have the ingredients. We've seen all the ingredients thus far for reliable transport protocol design, how TCP implements correct reliable transport using many of those mechanisms, what the congestion problem is, what the two high-level approaches are, end-to-end versus router-assisted or network-assisted, and we know that TCP takes the end-to-end approach, which means it only looks at packets and acts. How does it actually do it? How does it know how fast exactly to send to operate at a good point in this curve? which means to send as fast as you can without sending so fast that you screw yourself. How does TCP do that? How might you do that? How might senders decide how fast to send, but not send so fast that you collapse the network? The only thing is data packets and ACKs. I mean, these are things you've seen in your RDT protocols and go back and select the repeat step pipeline protocols. This is also, by the way, going to be a second programming project assignment to build a reliable transport protocol. I'm going to tell you how TCP does it, but how might you go about doing it? Yeah?
You send as fast as you can, and you on your timeout or too fast, slow down.
Yeah, so the answer is basically whenever the application says socket.write, okay, just pseudocode, whatever language it is. Whatever bytes it sends you to write, just optimistically go ahead, send it. Because if you're in this good regime, the more you send into the network, the more speed you'll get out of the network. If you don't even send, nothing will come out of the network, right? So optimistically, you can push your luck, basically send at the rate the app is sending data. However, if there's any sign of problem, just loss and delay. So loss is inferred using either triple duplicate ACKs or a timeout. Delays, you're getting delays with every packet. You use these two signals. If high delays are occurring, the loss is occurring, you back off, you slow down. That's exactly what TCP does. But it does it in a specific way. Because we need to be very respectful of the wrath of the network, because we've learned this the hard way, and we can bring it down to its knees. You can, right? I'll show you kernel code, where TCP's congestion control code looks like this big, exactly like the pseudocode you're going to see in this class. Your root on your machines, you can hack your kernel to change those parameters and send much more aggressively at the expense of other people who will see reduced throughput. But if everyone did that, we'll bring the network down to their knees, to its knees. So TCP employs a very specific approach where the high level idea is to increase your rate conservatively, but decrease aggressively at a sign of a problem. So it will push its luck. In the beginning, it will start with a low rate, not send as fast as the application tells you. That's too optimistic. In the beginning, even if the application is blasting data into the socket, it will actually not just optimistically try to push its luck and send everything. It'll grow slowly. And it'll continue this behavior throughout the lifetime of the connection, where at any point in time, if it's sending at 5 megabits per second, it'll try to push its luck to 6, maybe 7, or 5.1, 5.2, 5.3, 5.4. A packet got lost, 2.5 megabits per second, 2.6, 2.7, 2.8, 2.9. Sign of problem, 1.2 megabits per second. This is just this hypothetical example. Carlos.
Is that why, like, when you're measuring your download speed or upload speed, like, it gradually goes up? To the extent that they did it all?
Just in any general web download, you mean?
Yeah, like, if you're, like, trying to measure your network speed, like, so put your website to do that, it always, like,
That's a slightly different problem. To measure network speed, you are basically trying to measure this point, right? The capacity of the network. In that case, well, there's a capacity of the network and there's what a typical TCP flow can achieve on that network. So when you go to like bandwidth place or just any of these bandwidth test sites, I'm sure you've visited one of these, right, to check how fast a network is. They are trying to they're using typically something between what a typical one TCP flow can achieve on the network versus what's the most you would get out of the network. So they'll typically employ multiple TCP flows to get an assessment closer to the capacity of the network. Okay. in what we are seeing right now is not necessarily to assess capacity of the network. If there's one flow, one router, right, then we're trying to use all of the arguments per second capacity of the router. But if there's many flows, many routers, what each flow gets at any given router, what share of that router's resources it gets, that has to be distributed fairly, and that's a slightly more complicated problem than just measuring capacity, right? But one answer to your question also is one reason why when you do web downloads, for example, right? You use BitTorrent, you could just do a client server download. It shows you this marker that says 5 minutes left, 4 minutes left, 3 minutes left for the download to complete. And it's not intuitive. It'll go down to sometimes 3 minutes left and then go back up to like 7 minutes left, and you're pulling your hair, right? You just said 3 minutes left, and I was going to wait to go to school before closing my laptop for it to finish, and now you're saying 7 minutes, right? Why is that happening? Because it's changing. The network is changing in real time. The speed at which TCP is sending or receiving is changing in real time. So, a few seconds back, it looked like that rate was very healthy and it's going to only take 3 minutes, but sorry, time has changed. Now I'm sending much slower. So this is your TCP reacting in real time to network changes, to network congestion. So here's what AIMD is about: additive increase, multiplicative decrease. So we don't push our luck and send as fast as possible. Instead, we push our luck very slowly. Send us an increase rate until packet loss occurs, then decrease sending rate and loss limit. That doesn't tell you very much, right? AIMD stands for additive increase, multiplicative decrease. Additive is slowly increase. Okay, 2.1, 2.2, 2.3, 2.4. At 2.4, if you see congestion, you halve down to 1.2. That's a multiplicative, halving. So that's what results in TCP's so-called sawtooth behavior that looks like this. Linear increase, it's also called linear increase, multiplicative decrease, right? Additive or linear increase, multiplicative decrease, where the rate at which it's sending as a function of time is linearly or additively increasing. But at this first sign of a problem, it's multiplicated by a factor of 2 or half. It's going down. So that's your additive increase, multiplicative decrease. That results in AIMD, or the sawtooth style probing by end-to-end TCP. What's that sign of a problem? Where it halves, that's a loss. A loss means a problem. At that point, it's going to use the loss as a signal of congestion. Half. That's AIMD. Multiplicative decrease is going to cut the window in half. Multiplicative decrease, so how is a loss detected? There's multiple ways in which loss can be detected we've seen in TCP. One is timeout, the other is triple duplicate ACK. Timeout is wait for a much longer time. Triple duplicate ACK is more responsive. That's the fast rate transfer mechanism. There is a difference in how severe, in the severity of those two signals. A triple duplicate ACK is not that bad a problem. It just means that one packet maybe got lost, possibly just reordered, not even lost, but most of the packets are coming fine. That's why you're getting acknowledgements, but the acknowledgements are stuck at one point because that one packet got lost or extremely delayed. A timeout is worse. It's like you're yelling into an abyss and nothing is coming back. That's much worse. You send a train of packets, you're not getting any acknowledgements at all. That's when at some point you have to time out and then retransmit. So it's a much worse signal. And so we have different responses for triple duplicate ACK versus timeouts, because they are different in their severity of the level of congestion they are indicating. TCPs have evolved over time with different names, and for some reason it's it used to be much more fashionable in the previous century to name TCP flavors with names of cities that had casinos in them. I actually forgot what the reason was. I think most of them were coming from the west or southwest. And so So Reno is the oldest variant and still largely the simplest way to explain how TCP works as it's running in all of our countries. And TCP Tahoe it has this differentiation between triple duplicate ACK style loss and timeout induced loss. That's much more severe signal. So our responses are different. Upon a temporary problem like triple duplicate ACKs, we're only going to halve like an AIMD. But upon a timeout, which is much worse, we're going to come all the way down to a window size of 1. What does a window size of 1 mean? Window size of 1 means 1 segment or 1 packet. Segment, packet, same thing at the transport level. What is, like we were not talking in terms of packets in TCP. We said, go back and select the repeat, we're using packets. In TCP, we count bytes. So what are these segments? Well, even these bytes are being packed into segments that cannot be too big because there's an MTU, or maximum transmission unit. That's the network layer. At the transport level is for maximum segment size that limits how much you can send. Right? For UDP, you found some numbers for how big a datagram you could send. That's your transport level size. TCP is going to be limited in 1 packet by that size, and then the network routers may impose an additional limit that could be smaller than that. So TCP is going to send these, it also works in segments. In these segments, it's packing the byte stream bytes. And its window is maintained, it's counted in 2 ways. It's for some parts it's counted in bytes, and some parts it's counted as segments. So we'll look at these calculations for how TCP's throughput works with these segments in bytes. Okay. AIMD, why AIMD? So why are we choosing AIMD? Why not, there's many other ways you could do, even if your design goal was conservative increase, aggressive decrease, right? Be scared of annoying your network. There's multiple ways you can do this. Linear or additive increase, multiple increase is a very, very specific way. There are indeed entire other families of functions that have been explored for how TCP could possibly behave. This is a very, very important problem. Like, it gets to the heart of everybody wants speed, so it gets to the heart of what people want. Right? The second most important thing they want from the network is speed. The first is unfortunately available, right? Doesn't work at all. It's working, they want speed, and people pay money for this. So it's been very, very, very widely studied, a problem. And AIMD has some very nice properties. It's simple, and it is simple in sort of this mathematically formal way, in that it has some very nice properties. If everybody does AIMD in this completely distributed manner, where my TCP, without knowing about the presence of any of your TCPs, any other TCPs in the network, clearly what I'm doing from my machine, I have no idea what my neighbors are doing, leave alone what people in other cities may be going through the same Massachusetts routers may be doing. I don't need to know any of that. It's a completely distributed algorithm where if everybody does this, the network as a whole will converge to a sweet spot. What is that sweet spot? That sweet spot has 2 goals. One is efficiency, the other is fairness. Efficiency means resources shouldn't be wasted if there is somebody wanting resources. If a router has resources and there is somebody who could be sending more bytes through there because they have demand, you better not waste. You better find a way to use those resources. You better find a way to increase the rate through this router. They will not be able to do that if they're bottlenecked elsewhere or your protocol is too weak, too conservative. So that's efficiency. You also don't want 1 or 2 TCP flows to hog most of the bandwidth at critical points in the network. So like, there are some very key points of transatlantic cables. They're few and far. They go carry much of the traffic between US and Europe across the pond. So if there's there's generally a large number of flows going, TCP flows going through it. You want a fair share of these TCPs. Even at home, you probably have had arguments with your siblings at some point about, And you trying to do work, them watching a Netflix movie and, you know, not working out for you, or your application getting interfered by or you bugging your sibling or you playing a high definition game and they're trying to do something that's more interactive, that's also interactive, and they're getting a reduced quality of application experience. You want fairness. What is this fairness? Well, TCP is going to give you a fair distribution of throughput at the micro level as well as at the macro network wide level. We're not going to go into the mathematics of this. That's something I cover in a graduate course, but it has these nice properties. And we'll see a little hint of these nice properties in a little bit in this chapter. Okay, so how do we implement this with bytes and segments in TCP? Right? It is indeed byte counting. So in this example, irrespective of whether you think in segments or bytes, it looks like TCP's division of bytes or segments into what has been acknowledged, the frontier up to which everything is acknowledged, and then followed by things that have been sent but not acknowledged, things that could be sent but not have been sent, and then things that couldn't be sent. This fundamentally looks similar to go back, right? So that's what this picture shows you. The C window is from everything starting from the first outstanding segment until everything you could possibly send. That's our window. That was the N in go back in. Okay, so that's what the C window is. The C window is generally measured in bytes. Okay, so that's our last byte acknowledged, cumulative. Everything up to that has been acknowledged. These are bytes that have been sent, not acknowledged. This is the last byte that's been sent, followed by a set of packets that could be sent within the window. Our constraint, C window is a variable. Parameter in the kernel, at least the Linux kernel, is literally called CWND. The constraint is the difference between the last byte sent and the last byte add. Right? So, in this picture, your last byte sent is this byte, the last byte add is 6 bytes, so this is the outstanding portion. That should always be less than this parameter called C window we're maintaining. We are adjusting C window, we'll grow C window conservatively and aggressively drop it and use it to constrain that difference. So that's how TCP is implementing its condition control protocol. How does throughput in bits per second depend on this parameter C window? Well, TCP is sending, C window is measured in bytes. So in this picture, this looks like packets, but if you see a parameter called C window, it's generally measured in bytes. You don't count that in packets. That's TCP's sending rate, 10 megabits per second, 3 megabits per second, 40 megabits per second. The bits per second sending rate is C window over RTT. C window is the unit of bits or bytes, RTT is the unit of time, so that will give you a bits per second rate. Every round, or every RTT, you're going to send that many bytes. Okay. In a pipeline protocol, we would say we can send up to n segments every round trip. Right? So it's n segments is worth of bytes per round trip time. That's what it's sending. Okay. So AIMD is being used to manage that C window protocol, the C window parameter. Now, AIMD is not the only thing that's happening in TCP. AIMD is good, but it's kind of too slow. However, I said that the original approach of, well, why is it too slow? Well, in the beginning it's too slow. If you just start with one segment, what is one segment? Let's say 1500 bytes is a typical network NTU, maximum transmission unit. 1500 bytes is 12,000 bits. If you start with one segment per round trip time, you're saying 12,000 bits per round trip. Let's say a round trip is 100 milliseconds here to the West Coast and back-ish. 0.1 seconds. 12,000 bits every 0.1 seconds. Okay, that's our initial window. So if our initial window is 12,000 bits, our initial throughput C window over RTT is 12,000 divided by 0.1 seconds. It's 120 kilobits per second. 120 kilobits per second these days is not very much. So you'll start with 120 kilobits per second. Next, go to 2 segments, that's AIMD, increase by 1, and then half. Go to 240 kilobits per second, 360 kilobits per second, 480 kilobits per second. What's after that? 600 kilobits per second, 720 kilobits per second. We are still not even at 1 megabit per second after 6 round trip times, which is about half a second. So if you are on a high-speed network, you have a GBPS, you may have a 10 GBPS network. You can take a very long time for a TCP flow to simply increase its way to coming anywhere close to using the capacity in the network. So you're basically stuck somewhere here, because you're very slowly increasing. That's too weak. What else do we do, right? We don't want to ignite the wrath, the fury of this network that can bring the whole thing down to its knees. So we don't want to start by sending as fast as possible. That can be too aggressive. So TCP strikes a compromise by using AIMD for most of the time. That's a steady state approach. But in the beginning, it does something faster and cleverer than AIMD, which is more aggressive. But not as aggressive as sending as fast as you can right away. And that more aggressive mechanism than AIMD is called TCP slow start. Okay. It's actually much more aggressive or faster than AIMD. The reason it's called slow start is because in the beginning there was nothing. In the beginning it was just blast as fast. Whatever the application says, just blast it out. So compared to that, it's slow. Compared to AIMD, it's actually very aggressive. What's happening in AIMD? What's happening in slow start? Instead of additive increase, 1 segment, 2 segments, so 120 kbps, 240 kbps, 360 kbps. Instead of going 1 plus 1 segment every round, slow start is doing multiplicative increase, so it's doubling every round. 120, 240, 480, 960, and so on. This is exponentially increasing over time as 2 to the n segments. This is very aggressive. AIMD is linearly increasing. Okay. So that's what it's going to look like. It'll always start with 1 segment. So 1500 bytes is your network MTU, or 12,000 bits. It's very common. Then every TCP is going to start with 1 segment in the beginning. Well, not literally every TCP. TCP Reno, we'll see some implementation adaptations in more recent fields like Qubit and Quick. It'll start with 1 segment and double its way to, when it gets an acknowledgement for the first segment, fine, it's going to send 2 more segments out. When it gets those 2 acknowledgements just fine, it's going to send 4 segments out. If it gets those 4, 8, 16, 32 segments and so on. So in segment land, it's doubling as a power of 2. In byte land, it's just the bytes being corresponding bytes are just multiplied by the number of segments times packet size. So that's slow start. So in the beginning, it's very quickly jumping up its rate. And so whatever is the capacity, even if you have to go all the way up to a 1 Gbps network, a capacity network, a 10 Gbps capacity network, exponential, we in computer science, we know to respect exponential, right? They grow like crazy and they can become really huge numbers, unimaginably huge numbers. You'll, in logarithmic time in the capacity of the network, you'll very quickly ramp up and saturate the capacity enough to start experiencing loss, at which point you'll go back down. So we're not starting by sending as fast as we can. We're not being really, really slow like in AIMD. We are initially starting with slow start, that's an exponential increase, and then sort of shifting gears at some point into AIMD. That's what's happening. Okay, so initial rate is slow, but it ramps exponentially fast. So the question is, when do we shift gears? How do we go from like this, ramp up more from first gear to 3rd, 4th gear? Well, higher gear numbers mean look like power. The analogy breaks from automotives to so pictorially, this shows you that transition from the exponential increase. The exponentials look like that, right? Linear increase looks like that. On the x-axis here is the transmission round. So that's like an RTT. it's not, in practice, it's not quite an RTT, because there's queuing, so it can be a little more than RTT. RTT is just the light speed delay, there's no congestion, right? But let's, for simplicity, just think of, in this picture, around as either an RTT or more accurately, the time from when a train of packets was sent until the corresponding acknowledgements were received, so that you can decide what to do with the next round, how fast to send immediately after. So the question is, when should the exponential switch to linear from slow start to AIMD? And the answer is when the C window gets to half of its value before the timeout. So initially, there is a parameter called SS thresh, slow start threshold. A common default value for this parameter is 4 kilobytes. Okay, this is a platform dependent value. So one segment is 12,000 bits, right? For an MTU of 1500 bytes, which is, I say, fairly common. So you may be able to increase from 12,000 bits or 1500 bytes all the way to 64 kilobytes if that's the slow start. Until then, you can keep on doubling. Once you hit that slow start threshold, which initially starts with a platform-dependent constant configuration, but will also dynamically change soon. Once you hit that initial point, you go to linear increase, like in showing this picture. And then, this transition happens even without any loss or triple duplicate act. You just hit that slow start threshold. Once you hit the slow start threshold, there's no exponential doubling anymore. You have to increase one segment at a time. After this, at any point, if there's a loss in this AIMD phase, it's going to cut down its current window to half of its previous sending rate, and then set the new SS threshold to half of the window just before the loss. Right, so it's the loss event SS threshold is set to half the window. So how is this working exactly? Let's look at a concrete example. You started with 1500 bytes. You kept doubling, 1500 bytes per round to 3000 bytes per round to 6000 bytes per round, 12,000 bytes per round, and let's say you could go up to 64,000 bytes. That's the SS threshold. So you kept doubling to 12,000, 24,000, 48,000. You couldn't double up to 48,000 because 64 is where the SS threshold is. So you will stop at SS threshold of 64, and from there you're going to increase 1500 bytes at a time. So 64,000 to 65,500 to 67,000 to 68,500 and so on. Let's say you keep on going like this and go all the way up to 400 kilobytes of a window size. At that point, you encounter a loss through a triple duplicate act. If it's a timeout, you'll come back all the way down to 1. But if it's a loss, you'll halve. A triple duplicate action for a loss, you'll halve. So you go up to 400 kilobytes, 400,000 bytes. SS thresh right now is here, 64 still. When you halve, you go from 400 to 200 kilobytes. And SS thresh is set, increased now to 200. The value of the sending rate just before the loss, just before the halving. So if now there's a timeout, the new SS thresh is 200 kilobytes. It increased from 64. Now if there's a timeout and it goes down all the way to 1, it can now exponentially double its way until 200 kilobytes. So the SS thresh starts with a constant, but on a 10 Gbps network, the SS thresh should be somewhere in Gbps. So you can up to maybe 4 Gbps, or whatever its value is, it'll be in that ballpark. It can exponentially ramp its way all the way up, not just to 64 kilobytes per round. Okay, so there's loss. If there's a timeout here, we go all the way back to down, all the way back to 1. And here you can see in this picture that this time it is exponentially increasing until, in this example, SS thresh actually decreased. In my example, SS thresh increased from 64 kilobytes to 200 kilobytes. In this example, it's decreasing from 8 to here, it's 6 because it's half of the value just before the loss, right? So at this point, loss happened, window decreased from 12 all the way down to 1. But timeout happened, so window decreased from 12 all the way down to 1. SS thresh was set to half of the value just before the loss, which is half of 12, which is 6. Now you can go from 1 to 2 to 4. From 4, you can't go to 8. So you stop at 6 and then go at 7, 8, 9, and so on. So SS thresh is a dynamic value that can both increase, it's decreasing. In this example, I just told you how it can also increase, that adapts according to available capacity levels in the network that allows TCP to slow start its way up to SS thresh and then additively increase, get to AIMD phase after that. That's a summary of TCP congestion control. This is a finite state machine because we love finite state machines, right? Being sarcastic, I think most of you hate finite state machines. It's the finite state machine representation of our reliable transport protocol. But it's like, think of it like vegetables, okay? It's computer scientists, what's a Turing machine? A Turing machine is a state machine. It's the very abstraction of the computer. That is how we think of protocols. It's the right way to be able to prove protocols, right? It does get very abstract very quickly, so we are much more comfortable in code land. This is a very simplified finite state machine of TCP congestion control. It's not comparable to the RDT protocols, okay? You start out with slow start, where in the beginning there's no event needed. C window, CPU1 MSS, SS thresh. Usually 64 kilobytes is a common default, but that's platform configurable. You're measuring loopback counts, nothing has happened. In slow start, every time you get a new ACK, an ACK acknowledging new data that pushes the same base, you will increase as C window to C window plus MSS. Why is this C window plus MSS and not 2 times C window? If upon every ACK, let's say you're saying 4 segments out, every ACK you're increasing it by 1 segment. By the end of 4 ACKs, you will have increased it by 4 segments, doubling from 4 to 8. So this is per ACK action that is counting. This is essentially doubling every round here if you do this. If C window is greater than SS thresh, you don't do any action and jump to congestion avoidance, where you do AIM, additive increase, multiplicative decrease. But upon every new ACK, you're not increasing by 1 MSS. If you do that, you're doubling the window by the end of the round. Instead, you're increasing it by C window plus this value MSS times MSS over C window. This is less aggressive. This is increased by 1 second. Oh, I guess we're at time. So continue with this on Tuesday. Homework for no grade. Look at this episode carefully. There's a bunch of clicker questions coming for the first thing.